All right, guys, 5.5, very important. We're going to spend a little time on this right here. I'm going to tell you right now, chapter 5 is probably not going to see a test, okay? But you're going to see some optimization problems that come outside of this text and involve this. So guys, really the big part that you're going to be working on, that'll be kind of like a project almost, will be involved some of this optimization that we're going to talk about here today. So guys, 5.5, my favorite section to teach in calculus is optimization involving modeling, okay? The question we're trying to answer is how do we use, what's the word here?
Derivatives.
Derivatives. We've been talking derivatives for a long time. To calculate minimums and maximums with respect to geometry concepts. So we've talked about finding critical points. Critical points are where the first derivative is equal to what value? Zero. You have either a local maximum up here or a local minimum on the bottom. So our job today, we're going to find some minimums and maximums of given situations. Who's done that already? We're going to look at some parameters to help us determine what is maximized or minimized. Basically, we're going to be writing things in terms of two variables. We're going to want to start to rewrite stuff in terms of one variable to understand what we're trying to optimize. When I say optimize, I'm talking about find a minimum or find a maximum. Now your problems are going to be set up really well. They're going to say find a minimum or find a maximum. They're telling you what you're looking for already. So when you write these, you'll be writing them, setting them up accordingly to find that. Third thing, optimize given situations. Okay? Guys, I want you to think of the word as optimize as like what's most efficient. All right? What's the word efficient mean to you?
Fast.
Means probably, okay, here's how I think about it. Getting the most done in the easiest way possible. Does that make sense? Okay, so you want to be efficient. Optimization I think of as what's the most efficient way to do this, okay? And really the only vocabulary you have today is optimization. You're either finding minimums or maximums of given situations using first derivatives, okay? We're trying to, when I say optimize, I think of optimization as getting the most efficient way possible. Okay? So if you can think of optimization as what's the most efficient way to do this, then that'll be good for you. All right? Now, this table is going to be pretty important. All right? This table right down here, pretty important. Tips for optimization. First of all, what's the first thing they tell you when we do tips for optimization? What's number one say?
Understand what you need to optimize first.
When I say understand we need to optimize first, you're going to be talking about situations where we're dealing with area, perimeter, volume, like that. Understand, am I optimizing a volume? Am I optimizing an area? Am I optimizing a perimeter? Am I trying to optimize a product or a difference? Understand what you're trying to optimize. Secondly, this is a biggie. If we're going to start doing optimization involving modeling or tying it to some geometric concepts, it's going to be pretty important to make some sketches. Okay? Make some sketches. All right? And then third, this will be a biggie. Try to write your formula you are wanting optimized in terms of what, kids? One variable. Try and get everything in terms of one variable. And then step 4, find critical points and evaluate at critical points and endpoints. We're really setting first derivative equal to 0 and finding some values that make this work. Okay? So guys, like I said, we've become almost experts on trying to find derivatives of stuff. So let's get started on this right here. Example 1 is finding what here, friends?
Two numbers.
Going to allow us a what?
Minimum.
Okay. Find two numbers with a difference of what?
36.
36. What's the word difference mean mathematically?
Subtraction.
Right? So we might have two numbers, x and what?
Y.
So I might be able to say, you know what? I know x minus y would equal 36. Okay? We know that already, right? Find those two numbers such that they have a minimum what? Product. Okay? We are trying to minimize a what? Right? Okay. Well guys, the two numbers that we're dealing with are gonna be x and y, aren't they? So with the product, I'm gonna write a function for p. The product is what we are trying to find the minimum of. The product would be equal to what times what? X times y. Okay? Alright, let's think about this. Alright, what did step 1 say to do?
Find two numbers with a difference of 36.
Okay, so in our tips for optimization, that table, that 4-step table there, what's the first step say to do?
Understand what you need to optimize.
We need to optimize our product right here, don't we? We need to find p prime, don't we? But isn't the product set up in terms of two variables? X and what? Okay. Step number 3, I believe, says rewrite the function that you're trying to optimize in terms of one variable. So I want to get p in terms of maybe just, be really nice if I had just what over here? X, but I've got x and what? Okay, so here's what we do, kids. We come back to what we already know over here. This is what you know, isn't it? Is it possible to get y alone? Is it possible to get y alone? Would you guys agree that if I subtracted x from both sides, negative y would equal 36 minus x?
Yeah.
Okay, isn't that like negative 1y right there, kids?
Yeah.
Okay, so if I divide everything by negative 1, isn't y really going to equal negative 36
Plus
plus x? So if I rewrite this, isn't my y value really equal to x minus 36 right here? So kids, if y is equal to x minus 36 right here, based on what you already know, is it possible to rewrite this y value in terms of x now?
Yeah.
So I'm going to call this product that we're trying to minimize p equals that first number, x times, what are you replacing y with now?
X minus 36.
X minus 36. My friends, here's the deal. Have I been able to write the product of which we're trying to optimize, in this case minimize, all in terms of x now?
Yeah.
Okay, could I have written it in terms of y?
Yeah.
Absolutely, I could have gotten x alone, and as long as you've got the same variable over here on the right, you're good to go. So I'm going to start this. I'm going to say p is equal to
X squared minus 36x.
okay, you guys help me with the math. Once you have your product formula written in terms of one variable, p is a function of x in this case, we're ready to solve this. Find your critical points. In other words, first derivative set it equal to what?
0.
Well, what's p prime going to equal here, kids?
2x minus 36.
Okay, you found the derivative. You're going to take that 2x minus 36 and set equal to what value now?
0.
0. Okay? So, solve for x. What are you going to do to both sides? Wouldn't 2x equal 36 from that?
Yeah.
Divide both sides by 2. What's your x value?
18.
Okay. Something doesn't seem right here. All right, what's y equal to then? How are you going to find the y value?
You're going to have to plug it into the original equations.
Couldn't I just plug it in right here to find the y value now? So won't y equal x minus 36? Okay, have you guys got that y value yet?
Negative 18.
Yeah, when you put that back in, you're going to get negative
18.
18. You bet. Okay. right here, guys, we knew that x is 18 right here, right? Now, from what we knew over here, wasn't y equal to x minus 36? So from this now, we could say y would equal the 18 minus 36, which is what value?
Negative 18.
Okay, so here's the question. If you have two numbers such that their difference is 36, I want to know which of those two numbers, x minus y equals 36, gives you a minimum product. Turns out the values are x equals 18 and what?
Negative 18.
What if I extended this question and said, what is the minimum product then? What would you do? The product would be found by taking x times y, wouldn't it? Do we know x? Do we know y? So if I wanted to know that minimum product, 18 times what?
Negative 18.
Negative 18, which in our case would have been negative 324, if that's what they wanted to know. Okay. Let me show you something real quickly. The function that we came up with in terms of x, you might want to kind of highlight this right here. This was a function that we were trying to optimize, right?
Yeah.
Let me show you something in decimals real quickly. You will know you've written a function that's probably correct if the following happens. What did we come up with for a function?
P equals x times x minus 36, or x squared minus 36.
No problem. Let me just zoom in on this a little bit. Kids, the graph that I come up with, is that graph for that function that we're trying to optimize? We were looking for a what? Minimum product. Does the graph that we've come up with look like it's going to give you a minimum point? So you know you're kind of on the right track. If I click the graph right here, well, you check it out. What's the x value? 18. What's that minimum product? So it means that 18 and negative 18 have to be right there. Okay? All right, let's try some more here. Oh, I love this stuff. This is so much fun to me. Do you guys understand why we're taking derivatives now?
Yep.
Okay, taking lots of derivatives for a long time. Okay, let's talk about this next one. Okay. Number 2. That's where we're at, next page, right?
Yep.
You guys are going to talk me through this next one.
All right.
I think you can do it. Okay, this time we're finding what again?
Two positive numbers that have a product of 900. Oh, we're finding a minimum.
We're finding a minimum what?
Sum.
Okay, here's how I think you should set these up here first. Okay? Guys, what's the first thing we know here?
We know that two positive numbers have a product of 900, so
Okay.
x, y equals 900.
We would know that x times y has to equal 900. Okay? Now, this is what I like to write in the next column. What are we trying to, in this case we're trying to find a minimum, right?
Yeah.
I always just put up here, what are we trying to optimize? I always say, all right, what are we trying to optimize? Okay? Well, you guys just said we're trying to find a minimum what here?
Sum.
Okay, so the two numbers we're dealing with are x and y, aren't they? So what's a function for our sum? I might say s equals what? By rules of math, sum would be in the operation addition, right?
Yep.
We need to optimize the sum, but the problem is I've got the sum written in terms of how many variables.
2.
It would really be great if I could get this y out of here. So if I knew what y was equal to in terms of x, we could replace that, couldn't we?
Yeah.
So we go back to what we know when we give a variable alone. I can get x alone or I can get y alone. I like to get y alone. I just think it's easier to leave everything in terms of x. I could get x alone and plug it in here if you want to. Totally your call. You're going to get the same answer no matter what. I like to get y alone. What would y equal here?
900 over x.
Okay, so real quickly, kids, the sum that we're trying to, in this case, minimize would be x plus what?
900 over x. Okay,
here's your question. In this case a sum that we're trying to optimize, do we have a sum S written in terms of just X right here? Is that a good thing or bad thing? Okay, so we are ready to differentiate right here. All right? So, here we go. We're going to start with S prime. Now guys, I'm going to come to this point right here. This 900 over X, this is like 900 X to the negative 1 power, isn't it? Okay, so here we go with S prime.
It's gonna be
What's the derivative of X, my friends?
negative, oh, yeah, just one. And it would be negative 900 times x to the negative second.
All agree with your derivative? Okay, we're going to set that equal to what value now?
0.
Okay, set that equal to 0. All right. I don't like this 900x to the negative 2 power. So I'm going to call this 900 over what?
X squared.
So how about we do this? Cut that equal to 0. Is it okay to move the 900 over x squared to the right? So I've got 1 equal to 900 over what?
X to the second.
Could I multiply both sides by x squared here? So now we're at the point x squared equals 900, right? I don't know, you guys tell me, but what's the square root of 900?
30.
Could also be negative 30, right?
Yeah.
Which one am I going to use?
Oh, positive.
Yeah, it says we want 2 positive numbers, right? So the x value has to be what here, kids?
300.
Not 300,
Wait,
but
what did we say? 30?
30. Okay, I've only found one positive number, 30. What about the y value? How am I going to find the y value?
Plug it in.
Well, what was y equal to right here, my friends?
900 divided by x.
So y would equal 900 divided by 30, right? Which again is what?
30.
So what are our solutions here? What 2 numbers that multiply to 900 are going to have the smallest sum? 30 and what? 30 and 30. Okay? What would it be 30 again? Not almost 30 plus 30.
His joke or the math problem? Oh, okay.
You know, I was asked the other day to come up with 2 structures that hold water. And I thought to myself, well, damn. Come on, that's a good one. That's a good one.
Do you like have a dad?
Oh, I do.
book?
It's right on Facebook. They give me a new joke
Oh
every
my
day.
god.
Oh my gosh, yeah. Yeah, you just go type into the Daily Fun. It's some good stuff on there.
Facebook isn't
I can just picture a person, that's like part of his morning routine.
It is. You know, I'm building a new airplane. I'm gonna make it completely out of rubber. Okay? Gonna make it completely out of rubber. That one, when it crashes, should be safe. But you know what I think I'm gonna call the name of the company? Boeing or Boeing or Boeing. Guys, I had a lot of time to read lots of jokes. I've got a lot of them for you. Okay, let's talk about this one right here. Number 3 right here. Maybe make this example up here. Finding a maximum right here. This one here, you're probably going to want to make a sketch of this one. Okay, how about volunteer to read example 3 for me here?
Find the length and the width of a rectangle with perimeter 100 that will get you a maximum area.
Okay, so here's the situation. We're dealing with what type of shape?
A rectangle.
You know we're dealing with a rectangle, right? Okay, I don't know what the length and the width are, so is it okay to call the length x? Is that okay with you guys?
Yep.
And I'm going to call the width y. We know the perimeter is going to be how much, kids?
100.
Okay, here's what we know.
X times y is
Let's talk about the perimeter that we know. That means add all four sides up. So what would this be up here, kids? And what would this be?
Y.
Okay, so if I added all these up, how many x's do you have?
2.
You know that 2x plus 2y would have to equal what value?
100.
Okay, now, I'm gonna leave some room up here for that. What are we trying to optimize here? And I'm gonna put that kind of down here. Okay, what we're trying to optimize is the area. So guys, the area would equal what times what?
X times Y.
Okay, but my area is written in terms of two variables. So it might be a good idea to go back to what we know and get what alone. Okay, so let's get y alone. Okay, so we want to say, I know that all the way around here there's 100 feet of perimeter. I want to know how to make a rectangle so that we get the largest area on the inside of that. Okay, some people might just say, well, make it 100 and whatever's inside is what's inside. But some people will set this up in such a way that they get the most area inside. Okay, they're trying to set this up really in the most efficient way, aren't they? To get the most area out of what you have. Okay, so let's get y alone. You all agree that 2y would equal?
No, because you could have a perimeter of a bunch of make a bunch of edges, and it'd be a smaller area.
Okay. So help me out here. Divide everything by what? Won't y equal 50 minus x?
Yeah.
Okay, so my area function then, if y is equal to this 50 minus x, right down here, what we're trying to optimize, what can we rewrite in there for y?
50x minus x squared.
Yep, and you're a step ahead of me right now. I'm going to call this x times our replacement, which was what?
50
50 minus x.
Okay, you're going to learn something today, and this becomes a equals, this is like what you think you said, Ellie, 50x minus x squared?
Yeah.
Okay, so the question is this. We're trying to optimize our area. Have I been able to write my area in terms of one variable now? Okay, so help me out, guys. What's the a prime going to equal?
50 minus 2x.
Oh,
Right? And once I've differentiated, we're looking for critical points, so we're going to set this equal to what?
0.
Okay, so wouldn't this mean 50 is equal to 2x here now?
Oh, yeah.
So what's that make the x value, friends? X is going to equal 25, right? So guys, we've solved for x. Can we go back up to what we know? What did we say y was equal to up top there? 50 minus x, right? So based up here, y would equal 50 minus x, so what would y have to equal? Guys, if x and y are both 25, how are you going to set a rectangle up with a certain amount of fence to get the most area inside there? Turns out that shape is really a what? A square. All sides are going to be equal. So anytime, I don't know, I think all rooms in a house should be square. Because that's using the least amount of material on your walls, but getting you the most area inside of a house. That's the most efficient way to build a room. Make it actually, you want to know what the most efficient way is to make a room, given a certain perimeter?
I feel like this is going to be a joke.
Nope, it's not a joke. A circle will get you the most area with the least amount of fencing or
How would
outside
that even
perimeter.
be possible?
I'll show you someday. It's going to be fun. Okay? Every house should be a circle house. Now, I went to a school in Charles City. And in Charles City, because we were just really smart people up there, our school had a gym, a big gym, and then our high school was 3 circles. So you would have we had set up like a triangle. We had a circle area here, a circle here, and a circle here. Okay? I gotta tell you, when I was running track up there as a Charles City Comet, track practices indoors in Charles City made me dizzy.
You went to school in Charles City?
I did. It's God's country. Yep, north of Highway 3. That's where it's at.
What's north of highway?
Yeah.
Oh, is that what that joke means?
Yes.
I didn't
It's a
never ends.
family joke. People make fun of me because I'm from north of Highway 3. Everybody's like, once you get north of Highway 3, people are weird up there. And so, people in Mindy's family, my wife's family, make fun of me. So I turn it around and make fun of them. Are we on the next page? We are, aren't we? This is a great question right here. Optimizing dimensions. Number 4 is a little bit more in depth, a little bit more difficult, okay?
There's your circles person.
There's some circles there. Suppose the volume of a can is 600 cubic inches. Now the assumption we're going to make about our can is it's what kind of a can all the way through. Yeah, it's even, so it's a cylinder, so there's no like indentations. It's just going to assume solid cylinder, and it's going to be closed on both ends. You know the volume of a can is what? Okay. Now I'm going to make a note up here by example 4. We're going to start probably getting into some geometric formulas. If we need geometric formulas, what do I suggest you do?
Google.
You Google them. So if you're not sure about a formula to start with, I would strongly encourage you to search Google. Okay, now I'll tell you through these as we go through the notes, but you're gonna need to know formulas to make this work, okay? We know what here first, kids?
The volume,
Okay, well, the volume of a can is equal to what?
600.
Okay, so since we know it, so the idea here is this. We know the volume of a cylinder is how much? 600 cubic inches, right? So here's the question that we're really after about what we know. What is the volume formula for a cylinder? Anybody recall that?
Probably something to do with pi.
Got something to do with pi. Now, if you didn't know that, you would Google up volume formula for a cylinder, okay? And it's going to tell you it's pi r squared times the height. So I would know this volume of 600 has to equal the volume formula for a cylinder, pi r squared times the height. Okay? Now, it says what dimensions will minimize the amount of material use. When I talk about the amount of material use, this is kind of like a pop can. How much aluminum is there? When I talk about the aluminum, that's on the outside, isn't it? Okay, isn't that like a surface area being on the outside? Okay, so this is what we know up here. I'm going to write this down. We know this about this cylinder. Its volume is 600 cubic inches, therefore 600 must equal pi r squared times the height. The part we're trying to do is what's the most efficient way to make a can so that you're using the least amount of material? Here it is. Okay. So, anybody recall surface area?
Two circles
2 circles, so 2 pi r squareds
and then a rectangle.
plus 2 pi r h.
Yep, that's what I was.
Is that right? Sweet. Now, here's the deal. When you look at your area that you're trying to optimize over here, have you written this in terms of one variable completely? You got an r and an h, right? Now, how many times does r show up here? I would say that's a good thing. Leave the r's. Whatever shows up the most, leave them. So we should probably get what variable alone?
H.
So come over here, let's get h alone. So are you guys buying that h would equal 600 over what? Right? Okay, so let's rewrite our area formula in terms of one variable. So my area is going to equal 2 pi r squared plus 2 pi r times what?
600 over pi r squared.
Okay, quick question here. Kind of hard to see that, so I'm going to blow this up here real quickly a little bit. This part right here, what would this pi value do to this pi value? Right? What would this r do to one of the r's down here? So here's how I'm going to write my area formula, kids. Write this as A equals 2 pi r squared plus, okay, what's the 2 times the 600 gonna get you up top there? 1200. I don't like that r in the bottom, so I'm gonna write this as 1200. I'm gonna leave that one r that remains down there, pull it to the top, and write that as r to the first, but r to the negative first here, okay? Now the question is this, have I rewritten that in such a way that we've got that written in terms of one variable? Okay, so help me with a prime. Here we go. 2 pi is a constant out front, so the 2 times 2 pi would make what? 4 pi r minus
1200 r to over. You could just do it.
I can do r over, well, yeah, I'll do that next step, okay? Now we're gonna set that equal to what, kids?
0.
Okay. Now I'm gonna move this minus 1200 r to the negative 2 to the right and make it positive, is that okay? But do you guys agree that that 1200 over r to the negative 2 is like 1200 over r squared? Okay, so we're gonna have here 4 pi r equals 1200 over what now?
R squared.
Okay, let's multiply both sides by r squared to get that out of the bottom now. Okay, so what we end up with on the left is 4 pi r cubed now. So I got an r here and an r squared here, right? That's going to equal r squared would go away. Now, kids, I want you to be very careful on this because in cylinders, things get messy. And it only gets messy because your calculators are only as smart as your calculators are. When you do this, you might want to say, I've got to divide both sides by 4 pi. But when you take 1200 and divide it by 4 pi, when you hit that divide sign, put 4 pi in parentheses like that. So when you're dividing in terms of pi, make sure you put parentheses around anything with pi in it. Okay, so if you go 1200 divided by 4 pi, I have no idea.
This says 95.5.
Yeah, I like that.
Oh, I was like, yeah, where is it?
Like equals, or maybe not parentheses.
Yeah, 381.
Okay, so, or you can do 1200 and divide it by 4 first. Whatever that would be, 300, and then take 300 and divide it by pi. But the 4 pi's would cancel right here, wouldn't they, on the left? Okay, so our r cubed equals 95.5. So my question is, how do you find
I think I did something.
how do you find r now at this point? Cube root of 95.5. So anybody have cube root of 95.5?
Oh, I got it. Let me find the. 4.570.
I'll call about 4.57. Let's see. The volume was measured in cubic inches, wasn't it? So that means that radius would be 4.57 inches, wouldn't it? Okay, but what other dimension do we have to find as well?
The height.
Okay, guys, come back over here. Didn't you know the height right here from what you knew? Wasn't the height equal to 600 divided by pi r squared?
Yeah.
Okay, so if you went in your calculator and you went 600, oops, I don't like that color there. It's hard to see. So if I went 600 divided by, and I put everything in parentheses like this, pi times 4.57 squared like this. I want to show you something about your cans. Because the people that are making cans with canned goods in them are driving me nuts. Every time I go into a grocery store, I freak out about this. Let me show you why. Okay? Guys, we got a height of how much here? We got a radius of how much here?
4.57.
Take your radius and double your radius to get the diameter. It's 4.57 times 2. It turns out that all cans that hold stuff inside should be made in such a way that it's just as wide as it is tall. The height and the width should be exactly the same. That would cut down on the material used. And I walk into Hy-Vee and I see their can of tomatoes, and the tomato can is higher than it is wide. And I look at my wife and I said, that's wrong. I look at all those cans as I was shopping and I said, that's wrong, that's wrong, that's wrong, that's wrong.
Your wife must love taking you shopping.
The easiest way, the most efficient way to make a can would be in a way that its width is the same as its height. So to maintain that volume inside of what you want and use the least amount of aluminum or whatever that material is on the outside, that would be the best way to do it. Now, you're gonna get an opportunity to write a letter to somebody and ask why they do it that way, but turns out there's a lot of science behind it too.
I'd assume you've already wrote a letter to them.
Well, I have. You know what the cool part is?